Hello everyone. Today's topic is whirling or critical speed of the shaft with damping force. So let's discuss deflection of the shaft running with angular velocity omega with damping force. Figure shows a vertical shaft with negligible mass rotates with angular velocity omega. Here O represents the axis of the bearing about which shaft and rotor rotates. S is the geometrical center of the rotor and G represents the center of gravity of the rotor. Few assumptions made over here are shaft is vertical with negligible mass. Due to Magnus effect of the air on the shaft, damping force is produced which is proportional to the velocity of the shaft. Another assumption is deflection of the CG is not collinear with the deflection of geometric center. So point O, point S and point G does not lie on a single straight line. Let small m equal to mass of the rotor, y represent distance of geometrical center of the rotor from bearing axis, E eccentricity, small d diameter of the shaft, omega angular velocity of the shaft, small a represent distance between CG from the axis of the bearing. When shaft rotates with angular velocity omega about the axis of the bearing O, then some forces are acting. The forces are first, centrifugal force acting at center of gravity G of magnitude ma omega square along OG. Another force is restoring force produced due to elastic property of the shaft of magnitude K into Y, where K is a stiffness of the shaft due to transverse vibration. Restoring force acting at the point S along SO. Another force is damping force at the geometric center S in the direction opposing the velocity of the point S. The direction is downward as shaft rotates in anti-clockwise direction. This force basically produced due to Magnus effect of the air. Now let centrifugal force acting at angle alpha with the x-axis. Then its components are m omega square a cos alpha in x-axis direction and m omega square a sin alpha in y-axis direction. After equating all forces in x and y direction, we get m omega square a cos alpha equal to k into y and m omega square a sin alpha equal to cy omega, where c is a damping coefficient and cy omega is a damping force. Let's consider triangle GON and cos alpha equal to ON by OG. ON is equal to OS plus SN. OS is nothing but a distance between the bearing axis and geometrical center of the rotor, that is Y. Let's consider triangle GSN and angle GSN equal to phi. Then SN equal to E cos phi. Finally, we get A cos alpha equal to phi plus E cos phi, which is equation number 3. Similarly, sin alpha equal to Gn by OG and OG equal to small a. For triangle GSN, sin phi equal to Gn by GS, where GS is nothing but the eccentricity E. If you take the ratio sin alpha by sin phi, we get equal to E by small a, and finally we get A sin alpha equal to E sin phi, which is equation number 4. From equation number 1 and 3, we get m omega square into y plus e cos phi, that is equal to ky. And after simplification, we get cos phi equal to k minus m omega square divided by m omega square into y by e. Let y by e is equal to a. Then cos phi equal to k upon m omega square minus 1 into a. We know natural frequency is equal to root k by m, and from that k by m equal to omega n square. Let r equal to omega by omega n, then finally we get cos phi equal to 1 by r square minus 1 into a, which is equal to 1 minus r square divided by r square into a, which is equation number 5. Similarly, from equation number 2 and 4, we get m omega square e sin phi equal to cy omega, and after simplification we get sin phi equal to cy omega by m omega square e and ca by m omega. Now, as we know, zeta, that is damping factor, is nothing but the ratio of c by 2m omega n. And from this we get c by m equal to 2 zeta omega n. After substituting this value in above equation, we get sin phi equal to 2 zeta omega n a by omega, and we get 2 zeta a by r, which is equation number 6. Now take the ratio of equation number 6 and 5, that is sin phi by cos phi equal to tan phi, and tan phi equal to this value, and after simplification get angle value phi equal to tan inverse 2 zeta r by 1 minus r square. Once again take sin square phi plus cos square phi equal to 1 equal to this value 2 zeta a by r whole square plus 1 minus r square whole square a square by r raised to 4. After simplification, we get the value of a, which is nothing but the r square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Once again put the value of a, which is nothing but the y by e, then we get y by e equal to r square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Now substitute the value of r as omega by omega n. We get finally net deflection of the shaft y as a function of eccentricity, frequency ratio omega by omega n. When there is no damping, it means zeta equal to 0. If we substitute this value in this equation over here, then we get y equal to e into bracket by omega by omega n square divided by 1 minus omega by omega n whole square, which is a deflection of the shaft in the case of no damping force. So this equation is the most general equation which can be applied in any case, shaft with damping or without damping. So finally we get the equation of deflection of the shaft as a function of eccentricity, as a function of frequency ratio and damping coefficient. Thank you.